Hi, my name is Julian Glover, and my poster is on the optimization of pole selection in the pole vault event. So I'd like to brief over my poster. So just to introduce my project, pole vault is a track and field event where a vaulter runs with a carbon fiber pole, and they put the pole into a box or a hole in the ground where the pole is then bent and the horizontal momentum is converted to vertical momentum upward to go over a bar. Now, there are a lot of differences in pole structure that are made to better fit a vaulter with their speed and their height and their weight. So those differences include the flux rating, which is just simply what materials the pole made out of, but a lot of them are carbon fiber. There are also differences in the weight rating, the pole height, obviously the producer of the pole. There's also differences in with the vaulter, including their speed, their height, where they grip, which is usually ideally the top of the pole. So poles act as a spring during this vault because they're compressing and then correcting themselves. So there's the law of conservation of energy, which states that energy remains equal in the system at all points. So in order to understand how to optimize pole selection to get the highest height possible, we have to assess the effects of each variable with what's ideal with the vaulter to find which pole they should use. So my review of literature, the first one is from the Physics of Pole Vault, and it just talks about, it was a research article, and it talks about how poles convert the horizontal energy to run into the gravitational potential energy achieved at the apex of the vault. So it's basically a transfer of kinetic energy from the vaulter to gravitational potential to get as high as possible over a bar. And a paper written about the physics of pole vault, or the energy transformations of pole vault, by M.P. Linthorne, talks about how poles contain elastic energy as they are being compressed, and again talks about the law of conservation of momentum, that they have equal momentum before and after, or of energy as well. So the problem that I looked to find a solution for was that a vaulter needs to understand the optimal amount of force to be applied into a pole. The goal was to find a relationship between each aspect of a vault and how it will allow a better analysis to find the optimum force on the best pole. So the hypothesis is that I found was that a greater weight rating would correspond with a greater release of energy, pushing the vaulter upward. And I thought this because I figured a greater weight rating would make the pole more rigid. It would have a greater spring constant in the pole, meaning it takes more force to correct itself, pushing the vaulter higher. And I also thought that a greater length would cause a greater release of energy, pushing the vaulter upward, just because with bigger poles there's more areas for energy to be absorbed and released. So for my methodology, first I set up an experiment where I chose 3 different poles based on their specific differences. So 2 of the poles had the same weight, 2 of them had the same height, and they all had very similar, they're both from similar producers made of the same material. And so the poles were bent to different displacements, and there was a force reader reading the force applied to get to each displacement. So the graph of force and displacement was used to find the spring constant of each pole, and the spring constant was used to find the trend in energy release for each pole compared to the force being applied. So you see the Hooke's law equation, F equals negative kx, have provided that x gets you the spring constant. And there's an image of the experiment and a description of each pole. So the results, I found that, I'll zoom in here. I found that pole 1 had an average spring constant of 18.44, pole 2 was 15.574, and pole 3 was 9.742. And then on the right here, I graphed that out using the equation for energy. And what I found was something very interesting, and something that I noticed in the experiment, is that there's something called a hysteresis graph, which is a graph that at points acts linear and at other points will act exponential. And that's what happened here. As displacement got past a certain point, it started becoming an exponential increase in energy, as well as, or as force reached a certain point, it started becoming an exponential increase in energy as well as displacement. So, my discussion was that a greater weight rating did correlate with an increase in energy release per unit displacement. I said that was likely due to an increase in the pole's rigid features with greater weight rating. Also, a longer pole had an inverse relationship with energy release, which went against my hypothesis. I said that was likely due to the increased surface area of the pole, which allowed for greater release of energy, as well as a reduce in the rigidness of the pole because it's longer, as it's easier to break a longer piece of wood than a shorter one of the same area, dimensional area. Displacement increased, and it reached a point of exponential increase per unit force applied, which is what I talked about with hysteresis graph. This implies that there's initially a gradual increase in energy release, but past a certain point, there's a sudden exponential increase, which in displacement, which can cause the pole to snap. I think that's exactly what happens. If a pole is using a pole that's too light, they'll put too much energy in it, it won't be able to correct itself, it'll snap. If they use a pole that's too rigid, they won't put enough energy in, they won't even get up, they'll just shoot back. So my future research, I want to find the correlation between a runner's velocity and applied force, and also velocity and energy. I also want to analyze the moment of inertia and the change in angular momentum in a pole vault system, and how the height of a vaulter can affect that. And as I stated before, my conclusion is that force after a certain point has an exponential effect on energy, and this can lead to a snap in the pole because they're storing force of the pole. It's too little. And also, my hypothesis was both supported and contradicted by the fact that greater weight rating did correlate with greater release of energy, but not with length. So thank you very much, and I hope you enjoyed my presentation.